and everyone should be here with me today. So the topic for today is the first ionization energy of the elements, and we discussed detail of that yesterday, what is happening, and even we discussed the boiling point also. Okay, so right now I'm going to give you some of the information about the first ionization energy graph. Okay, let me start this. So you can see here a graph is there in front of you about the first ionization energy. Okay, so I was telling you yesterday, for the first ionization energy or any of the ionization energy, you need to be very good in electronic configuration. Okay, so if you know the electronic configuration very well, you can understand this factor. Okay, so right now this is a very important topic, and I'm telling you, yesterday I was explaining to you about the helium, hydrogen and helium. What is the configuration of this? 1s1, and the configuration of helium was 1s2. That was the configuration, right? So to remove an electron from hydrogen is easy as compared to removing an electron from helium. That's why the first ionization energy for helium is lower, and the first ionization energy uh, for hydrogen is lower, and for helium is higher. Okay. Then we come to lithium. You can see lithium is here. So the electronic configuration for lithium is 1s2 and 2s1. That's the electronic configuration for lithium. So now to eliminate this electron is more easy because it is in the second shell. It is far away from the nucleus. A smaller amount of energy is needed. That's why it's difficult to break down a completely filled orbital as compared to breaking down the half-filled orbital. So this can be easily eliminated out. Now reaching to beryllium, beryllium is on number 4. The electronic configuration for beryllium will be 1s2 and 2s2. Now you can understand that if it is completely filled, the ionization energy should rise up. So this rise in the ionization energy is actually giving us an idea that the electron which is there in the s orbital to be eliminated, this one, it's very difficult. Now you see boron is there. The electronic configuration for boron is 1s2, 2s2, and now 2p1. Now you can see it's another subshell which is started. Okay, and this other subshell is in the beginning of it. That's why this is neither half filled, this is partially filled, and 2s is half filled. So to eliminate an electron from 2p is easy as compared to eliminating an electron from 2s. That's why there's a drop of energy. Okay, now you can see I have highlighted these points, Be and B, boron and beryllium. The examiner will be asking question about these points. Okay, so let me highlight those points once again for you. There will be a question about this area, there will be a question about this area, and this one and this one. Definitely they're going to ask you what happens to the ionization energy. Okay, between group number, beryllium is in group number 2 and boron is in group number 3. So between group number 2 and 3, 4, 5 and 6. So group number 2 and 3 and 4, 5 and 6, you are going to be asked about it. Now moving on to carbon, when you go to
Sir,
carbon, yes, please.
sir, they won't ask about the other ones.
These are the controversial ones. There's a drop. The rest of them are rising up. So rising up is easy to be explained, but the drop is difficult to be explained. So these are
Okay.
specific questions, okay, in the exam. Definitely you will be asked about everything, but these are specific ones by 99.9% chances of these points which I'm explaining to you. But it's all based on the electronic configuration, okay. Now you can see this carbon. The electronic configuration of carbon is 1s2, 2s2 and 2p. It is 2p2. Okay, now the more electrons are there in it, the more you're moving towards difficulty. And if you're rising up here, it means you're moving towards the difficulty. Now nitrogen is having 1s2, 2s2 and 2p3. 3 is half filled, okay? Half filled is more stable as compared to 2p2. That's why it is higher. Moving towards oxygen, you will find that the electronic configuration of oxygen is 1s2, 2s2, 2p4. Now, if I elaborate a little bit this 2p4, you will find that it is classified into px, py, and pz. Okay, one electron, and one electron. So there are 3 electrons which are facing up, and there is 1 electron left now. Now this is a highly stable condition. When P is having 3 electrons, highly stable condition. But when you are inserting the third electron here, then you are destabilizing this condition. This electron. So this electron here is not accepted by Pz, Py and Px. So what will happen? It will try to enlarge its size. Whichever subshell is there, that is going to enlarge its size. Right? Enlarging the size means that if this is the nucleus, the subshell has gone from this place to this place now. So it is bigger now, away from the nucleus. Force of attraction is less now, so smaller amount of energy is needed for this. Are you getting my point?
Yes.
Yes, sir.
So less amount of
Yes,
energy
sir.
is needed, that's why there's a drop. Okay. Now let me give you comparatively what I said to you about beryllium and boron and nitrogen and oxygen. The same argument will be applied to magnesium, aluminium and phosphorus and sulfur. Okay, but only the number of shell will be different. And if this one is 2s and 2p, 2s what do you call this? Yeah, 2p. The other one will be 3s and 3p. Okay, so I'll give you the argument once again. I want you to please focus here on it. Okay. Now, I have 2 points with me now. Okay. And those 2 points are this area and this area. Right? So, this is the most important point. Between these two, there's a drop and there's a drop. Now, this drop, the first drop, just focus on the configuration, and I'm going to talk from the configuration. It is 1s2, 2s2, right, beryllium, and boron is 1s2, 2s2 and 2p. 5 electrons are there in boron, right? 2p1. So between beryllium and boron, another subshell has started. Another orbital has started, subshell, right? The subshell or orbital P is away from the nucleus more as compared to S. That's why less amount of energy. This is away more, okay, from the nucleus. Okay, so that's why more energy is needed for it. For the less amount of energy is needed for boron. Okay, because it is away from the nucleus, so the force of attraction is less comparatively. When we talk about this one, so what did I say? I said another subshell has started here. So even in this case, another subshell has started here. Okay? That's why the other subshell is away from the nucleus, less amount of energy is needed, there's a fall or there's a drop. In this case, we have 1s2, 2s2, 2p. If this is 1, 2, 3, so nitrogen is stable while oxygen is, this is for nitrogen, this configuration is for oxygen, 1s2, 2s2, and 2p4. So the argument here is between nitrogen and oxygen that the fourth electron in oxygen is destabilizing the situation. Okay? In nitrogen, all the three electrons are happy. They're obeying the rules and regulation. They're living independently. But the fourth electron, which is coming now, this electron is to be accommodated. So the subshell is stretching a little bit. The atomic radius is increased a little bit, which needs less amount of energy. There is a drop in this case. Am I
Okay,
clear?
explain again between nitrogen and oxygen.
The electronic configuration of nitrogen is ending up at 2p3, where 2p is having single electron each subshell. But in oxygen, the fourth electron which is coming is unacceptable by the subshells. To accept it, the subshell should stretch a little bit. It will create a space a little bit, moving a little bit away from the nucleus, decreasing the force of attraction between the nucleus and this. And
So the subshell will expand.
yes, of course, there's no other way then.
Okay, sir.
So the force of attraction is dropped down and the ionization energy is also dropped down.
Okay, sir.
Okay, are we clear with this?
Yes, sir.
Okay,
Yes, sir.
so just give me a minute. Okay, let me sign. If you have any question, you can ask. Why has helium the largest first ionization energy? Why helium has the largest first ionization energy? So you need to understand again, once again, when you are understanding this, you need to go on the electronic configuration. The first electron is in the first shell closer to the nucleus and has no shielding effect. We'll talk about the shielding effect also. Okay? And has a bigger first ionization energy than hydrogen. And it has one proton in it. That simply I have explained to you that the configuration between helium and hydrogen is that helium is having two electrons, which is a completely filled, and hydrogen is having one electron, which is half filled. Okay, and the common sense is that there's a common question here also. Why do the first ionization energy decreases down the group? When you are going the group, the number of shells are increased actually. Okay, so group number one, then group number
Distance
two.
nucleus increases.
So you can see the radius is increasing, and the radius is increasing because more and more shells are there. More shells. Okay. So when the number of shells are increasing, along with it, radius increase is also there. Right? So what is here the shielding effect? What do we know about shielding effect? What is shielding effect? See, shielding means to cover something. To cover. Okay. Now, when we are working on the shielding effect, we need to understand that when shell number 1 is there, okay, the electrons living in shell number 1. Let's suppose I am the electron living on shell number 1. I am very close to the nucleus, right? And this is another shell where two electrons are there. Now the inner electron will revolve around the nucleus. It will try to cover up the nucleus so much, it tries to hide the nucleus from those two electrons. This is called shielding effect, right? Now shell number 1 and 2, the electrons living there, they will try to hide the nucleus so that the force of attraction doesn't reach to this electron. This is called shielding effect. Shielding effect is always studied on the last electron, okay? When we are increasing the number of shell, another one, you can see that the shielding effect is highly effective now. See here. Now, shell number 1, shell number 2 and shell number 3, they are totally covering the nucleus together so that it is not seen by this one. So the force of attraction is reduced. So what I mean to say is, what is shielding effect? It is the covering of the nucleus by the shells from the outermost electrons actually. Okay. The inner shell, they don't want the electrons living outside to be attracted by the nucleus strongly because they are negatively charged, negative and negative and negative. So the negative cloud is going to be formed around the nucleus. And this cloud is affecting the force of attraction with the outermost electron. So the more the number of electrons, the higher will be this repulsive force. And why will be there more number of electrons? If there are more number of shells. So when you go down the group, the number of shells are increasing. Okay? You are getting more shells. So you reach to 7 shells actually. Or 7 energy levels. Right? So the outer electron, the one which is living on the 7th shell, it is having a repulsive force from 6 shells, from the electrons of 6 shells. They don't want him to be closer to the nucleus. Are you getting the point?
Yes, sir.
This is shielding effect. Okay? I'll provide you these notes also on which I'm writing right now. Okay? So this is shielding effect.
Sir, the electron in the outermost shell will cover all the other electrons.
No, 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 no. The inner electrons which are there in shell number 1, shell number 2 and shell number 3, they don't want actually, and there is a huge repulsive force for the outer electron. This is what shielding is. See this. I will draw something now again for you. This is shell number 1, right? This is shell number 2, shell number 3, shell number 4. Okay, so we got shell number 1, shell number 2, shell number 3, shell number 4. An electron living here is facing a repulsive force from this and this. These three are covering the nucleus completely. If nucleus is in the center here, this is the nucleus, then all the three shells They are covering the nucleus. This is shielding. Okay. So what about this electron? This poor electron is trying to be attracted towards the nucleus, but it can't. This force of attraction is reduced. So the more these hurdles are from the outer electron, and how many hurdles can be there depends on the shells. If I'm living on the last shell is 7th shell. So I'll be facing 6 hurdles. They will be covering the nucleus from me. This is shielding effect actually. Is it clear?
Yes, sir.
Yes.
Is this clear to you? Now the more the shielding effect is, the loosely the electron is packed. Okay? Yani this force of attraction is less if there is more shielding. Right? So more shielding, force of attraction is less. How much energy will be needed to remove this electron? Less or more?
Less energy.
Less energy will be
Less.
needed.
Less energy.
That's why when you go down the group, the number of shells which are, when you go down the group, the atomic radius is increasing because the number of shells are getting more. So that's why the electron is further away, the ionization energy is decreasing then. Right? Any question?
No, sir.
Okay. This was about shielding effect. Okay. Now moving to okay. Okay, why sodium has much more lower ionization energy than, you can see here the question. Why sodium has lower ionization energy, the first ionization energy than neon? So I'm going to focus towards the electronic configuration now. Now you see here, this is neon, look at neon, and this is sodium. So now coming towards neon and sodium, the number of shells are also different. Neon is having, because it is 2p6 now completed, okay, and sodium is 3s. So one extra shell is there in sodium. So the atomic radius for sodium is 1s2, this is the configuration 2s2, 2p6. See shell number 2, and sodium is having 1s2, 2s2, 2p6, 3s1. So the third shell has started. This is 2p6 which is completely filled. When you want to break down a completely filled orbital, you have to give it much more energy. Okay? Much more energy because it is highly filled, completely filled. And how much will be the energy in comparison? Like for example, if you're removing this electron, the amount of energy I'm supposing, if this is 500 kilojoules per mole energy is needed, okay, then the amount of energy for neon will be 10 times the first ionization energy of sodium. Okay, because you're breaking into a complete, that's why there's a big jump. You can see there's a big jump. So nearly 10 times will be that energy. And 10 times of 500 will give you how much? 5000 kilojoules per mole. Are you with me?
Yes, sir.
Okay. Now your course is giving you a graph which is showing the first ionization energy of different elements, and you will face another graph which will be showing the successive first ionization energy of the same element. This one is giving us a pattern. See this pattern, okay? It is about the outermost electron. Are you eliminating an electron from S or from P? Are you eliminating electron from 1s or 2s or 2p or 3s or 3p? Okay, so only the outer electron you're talking about. There is a graph of successive ionization energies as well. Okay, and that graph is telling us, for example, it's talking about eliminating electrons from sodium, all the electrons from sodium. How many electrons you can eliminate